SwayamPrabha. Digital India. Educated India.
Yeah, hello and good morning, everybody. I'd like to welcome you to this GIAN course on microstructure diffusion correlations in compositionally complex and high entropy alloys. And this will be taught by Professor Shankaran from IIT Madras and me. My name is Gerhard Wilde. I'm from Germany, from University of Münster. What we plan to do is to give an overview on high entropy materials with specific insight into their diffusion microstructure correlations. Why diffusion? You could ask yourself, right? Because I guess there are not many groups around who are doing diffusion work anymore. So maybe one could think, maybe old, boring stuff, maybe nobody's doing it anymore. But I hope to convince you and to show you that diffusion is a process which is everywhere, which controls, sometimes dictates materials' properties, materials' performance. And there is one additional point correlated between high entropy alloys and diffusion. Do you know what that might be? Sluggish diffusion, exactly, yes. So it's one of the four points that were mentioned, and I would say as a hypothesis, right? Because these alloys were basically suggested to really have a new approach to make materials by going away from the corners of the multidimensional phase diagrams into their center. And you can imagine that if you have the additional boundary condition or constraint that all of these different constituents, the elements, should be situated on a common lattice, that there are some outcomes in terms of the local structure, which is different from a dilute alloy like iron-based, aluminum-based, magnesium-based alloy, because now you have the interatomic interaction potential varying from site to site to site. And so this caused what people were thinking, the prevalence of very strong lattice distortions, because basically you can think of these interatomic interaction potentials like some springs which connect the balls, which we normally think of in a very convenient way as the atoms. And if they have a different spring constant everywhere, it means that the lattice is distorted. It's not like the perfect lattice which we used to think of if we think of, let's say, a nickel-based alloy, right? So you have the nickel lattice FCC, positions for the atoms are very defined, and from here, one position here, one position there, you either put a different element on a nickel site, or if it's a small element, you put it in an interstitial site. So you have local distortions, but overall the lattice is coherent, and it's very much similar to what we think of as the single crystal. In high entropy alloys, that's not the case. So we need to think of how does it affect microstructures, how does it affect defects, defect storage, kinetics of phase formation, stability of phases, and many of these issues, high temperature deformation, phase formation, phase stability, is directly correlated to diffusion, to mass transport processes in the crystalline lattice. And this is why we chose this topic, so microstructure diffusion correlations. Compositionally complex and high entropy alloys we put in the title. Do you know the distinction between high entropy alloys and compositionally complex alloys? Well, for high entropy alloys, we think of we go into the center of these multidimensional phase spaces and we have, let's say, 5 or more constituent elements, putting them together. And as I just explained, mentally we think of putting all these constituents on a common lattice. And what I describe now is a high entropy alloy approach. Right? So we have only one host lattice and we put the different constituents perfectly, ideally at random onto the different lattice sites. Now, very often we see that the phase stability, so it means the phase stability of the single phase solid solution where all the atoms are situated on a common lattice, is not enough, specifically at the lower temperatures. And so we get second phases. So we have maybe one phase which has 5 constituents of a certain crystal structure. Let's be, for example, FCC. But we have maybe also a second phase then, also having 5 or 4 constituents, but with a different crystal structure. Maybe, I don't know, BCC, for example, or HCP. And this is then what we call a compositionally complex alloy. So it's, again, a multi-constituent alloy, which has large solid solutions, meaning solid solutions at high content of all the constituent elements, but it's not a single phase anymore. Is there any, do you have any thoughts about why this could be important to have second phases? Is it good or bad? It's good, yes. Why? Exactly, the mechanical properties are there. You also wanted to add something? Yes, exactly. It will give strength. It will also give problem, because misfit can create stress concentrations, and by this you can open microcracks, and then if you have environmental effects like humidity, air or so, then this can start, for example, stress corrosion cracking, so the material fails, so the service lifetime will be impacted in a negative way. But normally we put these second phases in deliberately in order to make a material having higher strength. Why does it have high strength? What's the physical mechanism of a second phase making the strength go up? Exactly, dislocation glide is inhibited at boundaries. We have it already at the grain boundaries, right? So this is why Hall-Patch relationship works. So we get strengthening when we make the grain size smaller. If we now have a phase boundary, meaning a boundary between one phase, FCC, and another phase, BCC, it's an even much stronger obstacle to dislocation motion. And this is why strengthening is very, very pronounced when you introduce this alloying concept and materials design concept. But it also affects it in terms of creating problems if it's too strong in terms of dislocation blocking, because then stress concentrations again build up, and then you will have high strength, but you will not have a very ductile material. So it means it can fail in a brittle way rather early. So one always has to keep the balance. And this is what was thought of as one of the prime important features of high entropy and compositionally complex alloys, because we have so many set screws with the 5 or more elements that we can basically tune, in theory, almost everything, like the lattice mismatch between the two phases, the coherency at the heterophase interface, the phase boundaries, so that maybe it could be prevented that cracks form at the interfaces, that they are much stronger in terms of service lifetime, that corrosion cannot easily occur. And then again, sluggish diffusion comes in, because corrosion in the end is a diffusion process, right? So if you have sluggish diffusion, it means that your material will withstand much longer in aggressive environments. And this is why, for example, high entropy coatings are such an important topic, because you want to prevent the material from environmental degradation. But at the second point, you don't want to spend too much of the material, because when you make a real material, there is also one issue which we as a researcher often do not take into account, which is cost. If you want to apply it, it has to be cheap. And when you look at the high entropy materials that so far have been developed, and we will have a look at it in a minute, also throughout the course, then it means that most of these ingredients are not really cheap, right? And so one has to compromise service lifetime performance with cost, and coatings are a great way to do that. And this is why I think this has become very important topic today. I don't know. Okay, here we go. Yeah. So concerning the scope, I think you have obtained the scope. There was a change on the first days because Professor Shankaran has to be involved in these nationwide exams, and so this is why on day 3 and I will teach. Day 4, Professor Shankaran takes the course, but day 5, I am back to taking this course, and the lecture planned for day 5 by Professor Shankaran will be given on day 8. So we have just swapped our lectures here. When we have 2 lectures, we would normally start at 10. And then the second lecture, and this is up to discussion between us, we can start then at 11 after a bio break, or we can immediately go through. This is, for me, it doesn't matter, so it's up to you. We can take a vote later on, maybe after 45 minutes, and as we are in a democratic country, we can let the majority of the voters rule. I just heard that the 3rd lecture will not be at 14, probably because this is reserved for this course only up to 13. So on the days where we have 3 lectures, we will basically probably start at 9:30 and then have 3 lectures so that we fit into the slot. But we will let you know ahead of time because this is what I just this morning learned, so I have to discuss with Professor Shankaran. And we will have a duration of 45 minutes. And this is what I wanted to emphasize again. Questions and comments from your side are always welcome, as well as answers to questions I pose to you. So if we have a discussion going, I think it's much more rewarding for everybody, including me. So, but maybe also for you, even if there is a discussion on a question of mine between you guys, because I think this is what I do in my lectures back home in Germany. And I always have the feeling that the students and PhD students learn more if they discuss and debate amongst them, right? Because then you maybe see, conceptually I got it right, or I maybe have to look it up in a book a little bit deeper. There is a final exam opportunity for those who are taking part in presence. I'm not sure if anybody of you want to obtain a graded certificate. Maybe you can show me by raising your hand who wants to do it. 1. Okay, so this is easy to organize. Then we will just meet with you. And then there is no time restriction at all. Professor Shankaran and me have already discussed that we will sit together and then we will just have a discussion. This is like the way I do my oral exams back home. I will just sit individually with the students, and then there is somebody who also takes notes and who maybe helps us if we don't understand each other immediately, so that we have something like 30-minute discussion and questions, answers, and yes. And it will be after the last day of lecturing, obviously, if that fits your schedule. But since you're only one person, we can also go by your schedule. Okay, perfect. Yeah, let's do that. And then you will get a grade and a certificate and everything. So very good. Then this is already done. Then maybe some words according to my own person. So this is the outline of Germany. And we are situated here, University of Münster. It's very close to the Dutch border, so the northwestern part of Germany. And this is one of the 5 largest universities in Germany. So we have about 50,000 students. We have most of the topics, unfortunately no engineering, but I'm in physics, so materials physics is what we call in Münster this aspect. So this is my building. As of now, there's a new one built. I'm here in the 6th floor. And what we do is we are interested in nanomaterials, metallic glasses, internal interfaces, obviously high entropy materials, and then also internal interfaces in high entropy materials. And we also are part of the Center of Nanotechnology, a separate building where we do surface nanostructuring. Also partly related to these materials here, but partly also related to other topics like sensing or light harvesting, which we also do in my group. I'm also the editor-in-chief of this journal, and this is maybe specifically important for you young guys, because when you stay in academia, often as a young person, you don't have all the funding that the senior people have, and sometimes it's harsh to pay for the publications, also paying for reading the publications. And this Beilstein Journal of Nanotechnology, which is also covering nanomaterials, internal interfaces, and so on, is a diamond open access journal. So it means nobody on this planet has to pay anything to read all the articles, and nobody on this planet has to pay anything in order to publish. But the peer review is very strict because we, as the journal, go for quality and not for quantity. And you could ask, how is this possible? Who pays for it? And nicely, Beilstein Institute, which is a charity foundation founded 60, 70 years ago by the German chemical industries as well as Max Planck Society, has put down money at that time. This is still kept, and from the interest of this money, the whole publication thing works. And yes, yeah. And yeah, it's really, I think we were one of the first doing diamond open access so that nobody really has to pay. And I think we are happy to have a broad scope. And yes, yeah, it goes from atomic force microscopy based research. It goes to nanomedicine. It goes not to sensing, energy harvesting, but also to nanomaterials on a metals basis, semiconductors. So it's really very broad. And as I said, the quality is very important. So it's about 75% of the submissions are not rejected, yes, yeah. But I think that's good because we have... Absolutely, yeah. And that's, in the end, the most important thing, yeah. Good. So if you feel interested, look into the web pages or contact me. I will be able to provide answers. And if I don't know them, then the managing editor, Barbara Isa, can explain everything. So let's go to the lecture. Development of high entropy alloys. I think it's starting now with kind of the history. And we were, when we submitted this course proposal, specifically asked by Gian reviewers to include this. I think it's nice because it's really a new approach, only barely 15 years or so in the making. And it's, I think, the first one since I was at your age that has really changed the paradigm of how to make materials, right? To really go and dive into the centers of these multidimensional phase diagrams. Could you imagine why not earlier? I mean, it's such an obvious thing to do, right? So you could have done it 30 years ago or 40 years ago, but why wasn't it done? Were people dumb? Or was there any development that helped going this way? Has anybody heard about CalFAT? What is it? Calculation of phase diagrams. This is, thank you very much. This is how it's translated, right? And it means that you can basically access thermodynamic equilibrium on a computer. You need all the input data. Most of the input data has been available over the last 50 years already because almost nobody's putting or creating real hard experimental input data anymore. But the computational methods and the computational speed calculating multidimensional phase equilibrium with all possible phases, including the metastable phases, has not been possible since about 15, 20 years ago. And I would say still we see every year it's getting more and more easy. You don't have to wait so long, because 10 years ago people had to go to a supercomputer, wait for a week to get a phase diagram. Maybe it was wrong, then you have to go back. Now you can do it on your own PC with the same cloud service, everything, yes, yeah. And so this is, I think, the major point why this was done really only such short time ago. Now, in this overview first lecture, I will talk about many aspects, but I will not go into detail because they will be detailed later on, right? So if you have questions, ask me, but if I say maybe wait until a future lecture, then don't be mad at me. Yeah, so I would go now with the definition. So high entropy alloys are alloys that contain 5 or more principal elements in near equimolar ratios. So the typical alloy which we know is the so-called Cantor system, because Professor Brian Cantor developed it. And it is basically really a mixture of 5 elements, and each element has 20 atomic percent. So that's the perfect high entropy alloy according to definition. There's often situations where we cannot easily mix all 5, 6 or more constituents really at equimolar concentrations, because maybe at that concentration another phase has a much higher lattice stability. So it means the thermodynamic driving force will favor this other phase to form, at least as a second phase. And then if we want to really have a high entropy system, only single phase solid solution, then the compositions need to be varied a little bit, so that it's not longer totally ideally equimolar, but it will be still having large relative concentrations, meaning that there is not a minority element present, but all of them are real alloying additions with equal rights, so to speak. And yeah, this has been introduced a couple of years ago, and I think it's really remarkable as a development, but also it shows that computational design goes nowadays hand in hand with experimental design. And you can also think of it like, if you are a PhD student, do you want to permutate 7 elements in terms of finding out which alloys you can make in a single phase solid solution? No, right? Because you want to finish in a given number of years. And so all these experiments you couldn't do at a sufficient detail, depth, and rigor. So computers can do this much more easily. And this is why this is, was waiting to come when the computers were available. But there were early concepts and ideas, and normally people say in 1950s to 90s precursor ideas have been formulated. And they were starting like with binary, ternary, quaternary alloys. Most importantly, the theoretical groundwork for multi-component systems has been established, and this has been gone into CalFET, right? I mean, this is what people mean by that. Actually, I looked up the literature, and as early as in the late 18th century, 1787 or so, there was already work on what we today call high entropy systems, because there was a German natural philosopher who tried to mix zinc, tin, indium, and these low melting elements in order to, I think in the end he wanted to make gold, but he wanted to just see how can a material property be changed and maybe improved by mixing all these elements together. It was not a systematic approach, so we don't call it science what he did as of today, but these ideas were around for quite a long time. Challenges are you can hardly predict without a computer phase stability, and also mechanical properties would be very difficult to put, and the computational tools for high-dimensional phase diagrams were limited and still are limited. So what we look here is a typical map of material science, not in terms of a phase diagram, but in terms of mechanical properties. I used to call them Ashby maps. So what you see here is fracture toughness signified by this Kc parameter, as a function of yield strength. And you see there are very, very different materials associated or put into this one diagram. So you have polymers, you have non-technical ceramics, you have glasses, normal glasses, not metallic glasses. You have all kinds of different things. Metallic glasses are over here. And you see high entropy alloys, many of them are actually on top of this. What does it mean? It means you can have a material that has rather large yield strength. This is what we often want to do, to have. Why? Because we can save weight in order to get structural stability that is sufficient. And it has high fracture toughness. And that is actually the important quantity if we want to design a material which has to withstand mechanical stresses. Normally when we do a test, like a uniaxial tensile test, we talk about ductility. Ductility is related, but often in a complex way to fracture toughness. But in real surface lifetime, fracture toughness is what controls when a critical crack starts to form, opens. Once it has formed, it's gone, it's over, goodbye. Right? So if you sit in an airplane, you see often the wings do like this if you are a little bit turbulent weather. Right? Actually, there are many, many cracks where the wing is situated and connected to the airplane, but they are all subcritical. So the Kc value is high enough to prevent these subcritical cracks to become supercritical. If it's supercritical, you don't want to be in the plane, because then the wing falls off very shortly, right? And so this is really a very, very important quantity. And you see high entropy alloys are on top of all this, so they are kind of a very ideal mechanical structural material. You also see it's a dashed line surrounding this region because we don't know yet. We don't know all the details. There are some investigations which have shown that some of the high entropy systems are in this region. But then you again have to take the cost issue into account, right? So for a structural material making large structures, the costs per kg is really important. This is why coatings and so on are maybe the way to go for high entropy systems, because cost is not in this diagram, but you know, iron-based systems are hard to beat. The steels are very good. By the way, steels. What if you have a very demanding mechanical application? So if, let's say, the cost per kg is not so important, still important, but not highest priority, but you want to make a material that can absorb shocks in a very good way. Let's say in a car, right? So your life should be protected by the car. If the car is hitting some other obstacle or other car, the car should take the damage, not you. So what would be a good steel? When you see really a lot of twinning happening in the material, that is typically happening in a range of strain rates, at high strain rates. So it means shock absorption, high strain rates. Twinning can be easily initiated because, you know, all the other processes are not as quick as a twinning transformation. Transformation-induced plasticity means there is martensite, austenite transformations occurring as a function or giving plasticity. And as a function of shock, they can also absorb the external stresses by creating deformation. And this means it can absorb, the material can absorb much higher kinetic energies by fast processes at high strain rates. And yeah, this is something which we also need to build up into the system. Yeah, you see high entropy systems are kind of in the literature, and you know this already, so it's constantly rising, the number of publications per year on high entropy systems. And interestingly enough, also on diffusion. As I said, diffusion is an important property, but not so many people do proper diffusion. And what do I mean with proper diffusion, I will explain in the next lecture, or maybe the second next lecture, because just to give you a flavor, many people put material A and material B together. Then they give it some time at some temperature. Temperature translates to kBT, right? You give it an energy for the atoms to become mobile. There is some Brownian motion, and there is a concentration gradient, because this is a different material than this. So interdiffusion will happen. Some atoms of this part will diffuse in this direction, and some atoms of this will diffuse in the opposite direction. Can you learn about the basic mechanisms of diffusion from such an experiment? Who thinks yes? Not exactly, exactly. It's not exactly, because the atoms A of this guy affect how the atoms B of this guy diffuse. This is what we call cross correlations, or cross terms in the diffusion matrix. So you have to think of this process of interdiffusivity controlled by the self-diffusivities plus the cross correlation terms. Onaga relationships are giving you the complete mathematical description. Yes, there is a solution model you need to take into account, but for the real atomic motion, you need to actually know how, for example, an atom moving from a material A into material B affects different atoms going the opposite direction. Because normally, another question to you. What is the typical process, the atomistic process of diffusion at high enough temperatures, if we think of typical interconnects between 3D transition metals? Let's say we have low concentration. We have, let's say, pure aluminum and pure nickel putting together. Maybe I can draw here my diffusion couple. I have to change first. Pen. Right, so when I put aluminum nickel here together, and I have a very atomically flat interface, put them together and put them at a sufficiently high temperature for a sufficiently long time. So I allow interdiffusion to happen. So after a certain sufficient time t, I have still aluminum on the left side, nickel on the right side, but I will have an interdiffusion zone. And if I now look at the interdiffusion zone and I plot something like, why is it doing this? No. I have a diffusion profile, right? So I have a region about here, where I have a mixture of aluminum and nickel. But how does it work? How can aluminum go to nickel and nickel to aluminum? What's the diffusion vehicle? What defect type? Vacancy, and I heard interstitial. Okay, so what do you guys think? Both could be possible in principle, right? Yes, exactly. Yes, and aluminum and nickel, have they different size, or are they having comparable size? Different sizes, yes. So could it be interstitial or we can observe the correlation, but for this system, it's really that the sizes are not sufficiently different, which means that if you put an aluminum atom in the interstitial lattice of the nickel, the strain would be too large. So it's energetically unfavorable. So this is substitutional diffusion. So it means it stays on one lattice. Both are FCC, right? But then you need vacancies. So vacancy mechanism is important. And this cross-correlation terms basically include how the vacancies bind to the different atoms. So a vacancy can bind differently to aluminum as compared to nickel. And this is also changed if the nickel is inside the aluminum lattice, or the aluminum is inside the nickel lattice, or if they are in the host lattices. These complex interactions are described by the diffusion matrix. And this is why from an interdiffusion experiment, we cannot easily infer the diffusivities that are talked about in high entropy alloys when they are called sluggish diffusers. Because that sluggish diffusion means the self-diffusivities are slow. They are supposed to be slow. And I will show you that this is not the case. So all the literature on this is actually wrong. But interdiffusivities can be reduced because of different binding energies to the vacancies. But it really depends on proper selection of your question. Like, is it slow for this particular element within the 5-6 constituents of the alloy or not? And so this is very important to keep in mind for later on, that diffusion, my old teacher told me, diffusion can be easily confusion because there are so many diffusivities, right? So you have to really be very precise, because self-diffusion, interdiffusion, tracer diffusion, impurity diffusion, it all means something different, and it has different boundary conditions connected to the term. So, microstructure of materials. I gather that all of you know about how to characterize, right? So you do optical microscopy or you do scanning electron microscopy, and you see different contrast arising from different optical properties, interactions, as well as different orientations. And I have to say, most of the high entropy systems have a microstructure that looks rather normal. So you have grains, grain boundaries. If you have two phases and you have a compositionally complex alloy, you have phase contrast, but there is not much more to it on this level. We will see later on that if you go to the transmission electron microscopy level, TEM, that things might be different because the defects of the crystal structure, dislocations, twin boundaries, and so on, are normally found in higher abundance in metallic high entropy alloys as in conventional alloys. So these systems can retain high defect densities to much higher temperatures over longer times. And this is giving you an additional set screw, because normally we use defects to engineer materials properties, right? And this is exactly what is happening here, even though it is not really recognized in the literature. So they can store defects in much better than conventional materials. Why is this? Well, we can only guess. I would guess it's because of these local distortions. So dislocation cannot easily move through the lattice because it has kind of a different Burgers vector everywhere, right? Because the spring constants are different at each position. And this makes storage of them more easy than in a perfect lattice of pure nickel. So. Yeah. Well, we depending on what you did previous to the material. So, but if you do a normal umforming process, so meaning you introduce quite a large deformation, you can easily go up to 10 to the 15. So it's really high. So it's actually often approaching almost to the theoretical limit. And it's very difficult to get rid of them. So if you anneal them at the typical temperatures, 0.75, 0.8 of the melting temperature for a few hours, you will see that the decrease in dislocation density is not very high. So they are really retained. You have to go to even higher temperatures, which if you want to get rid of dislocations is bad because it costs a lot of energy. So if you don't want to have the defects, then maybe high entropy systems are not a good choice because it will be very costly to make them defect-free or as defect-free as we can do a metallic material. Good point in time now to ask you guys for a vote. Should we have a break or should we go on? So who would like to have a break? Nobody? Good. Then let's just continue. Obviously, when we think of microstructures, we have to think of not only the faces that are visible, but you also look at defects, as we just discussed, and then also chemistry. And chemistry is what has mostly been discussed. Which compositions can we really use to make these high entropy systems? And I'm using high entropy systems now as a term for all these materials, whether they are compositionally complex systems with more than one phase or high entropy systems, just to keep it simple. But as you know, the distinction is there. In 2004, really the high entropy alloy concept was born, and it was pioneered by our colleague from Taiwan, Professor Ye. He published also the first really landmark paper, which is very highly cited, on high entropy stabilizing the single phase solid solution. Let me just see if you guys still remember the basic thermodynamics which you were taught. What do they mean with this term high entropy? Or where does the entropy come from? Excuse me? Yes, very good. Are there different types of entropy? Magnetic, electronic, there's all kinds of entropies. They are just talking about configuration, right? Very good. Why is entropy or high entropy and also high configurational entropy stabilizing a single phase solid solution? Exactly, right? So because we have this term, and this rules, right? So if we want to have a low Gibbs free energy, then it is helpful to have a high entropy term, and the configurational entropy is part of the entropy term. And so if you increase that, then you decrease G. And so in this competition between different phases that can be stable, the solid solution phase has an advantage if there is a high configurational entropy. And then it was shown that high entropy favors simple solid solutions. And people explored it. I think the alloy by Professor Cantor is probably the most important one in terms of research today. So most of the papers, especially the early papers, were devoted to this alloy. So So it's this alloy cobalt, iron, nickel, chromium, manganese. Each has 20 atomic percent, and this really gives you a single phase solid solution. When you think about the literature, is it single phase solid solution everywhere? Everywhere means each temperature, each annealing time. You're right, no. There are at temperature windows, lower temperature below 800 degrees centigrade, where second phase precipitates out. And that's showing you the concept is nice, having a high configurational entropy, but it works only if the temperature is also high, right? Because the product term, temperature times entropy, is really what you have to compare with the enthalpic term. So if you have either a phase which has a very high formation enthalpy, then you will not be able to beat it by T times S. Or if the temperature is too low, then this term will at some point become less than this term. And so you will basically have the solid solution break up into a multi-phase equilibrium. And yeah, this is maybe also important to keep in mind. All these enhanced properties are suggested. We don't know yet in many cases if they are there. So a lot of research by young people need to be done in order to find out. Yeah, this is really the concept, right? We have different elements, and this also already shows you that you have to now think of something like how to display phase equilibria, because you know from binary systems we are used to have a sheet of paper, A, B, and then you see the phase diagram. For ternaries we get different cuts through the prism, which is the phase diagram, but going to higher and higher number of constituents, it gets more and more complex, and we don't want to walk around carrying some, object. So we have to think of, and this we do down the road, how to really design concepts to show phase equilibria with multiple constituents and maybe also more than one phase present at certain temperatures, compositions, maybe even pressures. The point is really that we go here to the center of the multidimensional phase diagram with our approach. Yeah, we have seen already here, and this is just giving you a little bit more perspective on why we think that high entropy systems are over here. Because this is a very important alloy. Chromium, cobalt, nickel, so well known, for many, many years. And it has been really the starting point of making a high entropy system, because you can see that 3 of the 5 components of the Cantor alloy are already in there. You could see it's a solid single phase solid solution phase, and it has these very good properties. I would say actually it still has probably better properties than many of the high entropy derivatives, adding more elements, because the cobalt, chromium, nickel, or the cobalt, iron, cobalt, chromium, nickel, the quaternary without the manganese, is a fantastic engineering alloy. It has really very high fracture toughness, very high strength, and it has a microstructure you can design at will almost. So it means that if one thinks about the properties in terms of real world applications, I would say skip the manganese, right? Use this multi-principal element approach, but I would say the high entropy concept is not more important than looking really at performance properties, cost, value, lifetime, cycle lifetime. And so this is something one also needs to keep in mind. It's nice to have this new paradigm of how to make materials, but one should not be blind and say, oh, it must be 5 or more components. If 4 is enough, it's better. It saves money, it saves time, you know more what you do. And this 4-component system really is a fantastic engineering material. Yeah, and then you know that you have to basically think of many materials which have been done over the years. As I said, steel is a very good material, right? So you get very high ultimate tensile strength materials, and total elongation to fracture always follows this what is called banana curve. So if you want to have a very high strength, you probably have to compromise with elongation to fracture and vice versa. And obviously, the Holy Grail is going in this direction, right? So you want to really expand into the region where high strength and high elongation to fracture is happening. And some cases you can see that high entropy systems, for example, also steels with high number of constituents, they all have high number of constituents, but high number of constituents at rather high molar fractions can do the trick. But so I would call them, in parentheses, high entropy steels. They are not following really the definition of equimolar constituents, but yeah, some components, some number of components have high ratios. But costs. I mean, steel needs to be in industry cheap. This is number 1, 2, and 3 priorities. And so once you add cobalt or nickel or vanadium or so, you're out. So nice concept, but in reality and practice, it will not. It's not feasible, yeah, because industry will not be able to cope. Yeah, so this is obviously high configurational entropy, which promotes formation of solid solutions over intermetallic phases. I would question mark this. Why do I question mark this? Because intermetallic phases often have very high enthalpies of formation. And so you need to have a very large term T temperature times S entropy to beat the formation enthalpy of intermetallic phases. Temperature is limited by the melting temperature, so you cannot go up higher than the melting temperature, then you will not have a crystalline phase. And configurational entropy is limited by, you know, how many constituents can you mix at rather equal proportion. At some point you run out of elements, so it's maybe 6 or 7 or 8, but then you will probably precipitate out a second phase, and then it's not longer, you can no longer calculate the mixing entropy in the same way if you have a new phase. Then you have to do it for each phase separately. So the entropy will go down. One thing I wanted to say, I forgot now. And obviously, all of these are required in real-world applications. So if you want to make a material, it probably has to have at least serviceable mechanical properties. It needs to have resistance to oxidation and corrosion. It needs to have thermal stability, fatigue resistance in terms of its microstructure, and also, again, coupled to oxidation and so on. And so this is what we have to go through in terms of making really a new useful material, not just for basic research. And this is, I think, where high entropy systems are now currently at in terms of the state of research, that you can really now start doing research on finding appropriate materials which can be called engineering materials so that they can be applied. Because so far, most of the literature was really on basic knowledge about how do processes work in high entropy systems as compared to conventional alloys. Now, two alloy systems which you will see a lot in this course, and I have marked them and given them names as in the literature often done. It's the Cantor alloy, this cobalt, chromium, iron, manganese, nickel, 5-component equimolar system, and also the so-called Senkov alloy, which is the aluminum, hafnium, scandium, titanium, zirconium system. So they are true high entropy systems. They can be obtained as single-phase solid solutions. They have more, or they have 5 components. And this thing here signifies an artist's view of why they are important, because of lattice distortions. When you think of it, lattice distortions is all you need, right? Because when you think of any material property, you can always break it down in terms of applying quantum mechanics to the distance of atoms and the strength of the interatomic interaction potential. Whether it's a magnetic property, electronic property, mechanical property, in the end, it will rely on how do the two atoms which are close together attract each other and repel each other if they come too close. And this distance, which is dictated by the interatomic interaction potential, is governing density as a continuum property, macroscopic property, but it relates to basically any material's property. So if you go very rigorously, you can write an equation for any property relating it to the density. And so it means that sluggish diffusion and all these other things can basically be brought down and broken down to lattice distortions, to just the ability to build up a common lattice, host lattice, and put all these different elements close to each other at random at the defined lattice positions. And then all of it will follow from there. So it's not really 4 key properties of high entropy systems. And basically it is 3.5, 1.5. Lattice distortions and then this cocktail effect, because this just means something can happen which we don't expect. And this can be due to lattice distortions, maybe not. But so far there are not so many good examples of a real cocktail effect in high entropy systems. Maybe we didn't do enough research as yet. So these are the core effects. And as I said, high entropy, right? I mean, this is giving a name, right? So it's clear. What about local ordering? Let's say we have a 2D lattice. Let's say these are this is a Cantor alloy 2D atom 2D lattice, and I marked all the cobalt, iron, nickel, chromium just with these circles, empty circles, because they are so similar, right? So I don't care. They sit somewhere. Now I have a manganese also added in equal proportion, right? And this is now the filled circles. So this is, they sit here and there, arbitrary positions, but what? What if now I count atoms in the elementary cell and I find, for my basic FCC unit cell, maybe manganese always occupies the phase centers. Only locally, and then in like 10 lattice constants away, it will be maybe different, maybe not. Would that affect the material's properties in terms of entropy? It does, because if it's an ordered system, then it's not a random solid solution, then the occupancy probability for each site is not equal. And then I'm not allowed to calculate configurational entropy by just summing up for all elements. Then the entropy, the configuration entropy term is reduced. And this is what many people still are investigating. Is this the case for high entropy systems or not? It's very difficult to find out because you have to get the occupancy ratios for very similar elements. If they would not be similar, they wouldn't mix in a solid solution to begin with. And that means there is a lot of very high resolution X-ray absorption work or high resolution TEM analysis in a very quantitative way going on to find out, are these really random solid solutions, all elements placed at random positions of the same crystal lattice, or is there short range ordering, at least for one or more than one element present, which would reduce the entropy, configurational entropy, by this reducing also the stability, which we also observe in experiment. So one has to be very careful about what is entropy, right? Because it's not just if you take 5 elements together that you automatically get the configuration entropy as you calculate it in a simplified approach. No, you need to know exactly if they are randomly positioned on a given lattice.
What about L12 type high entropy? Like people have reported L12 structure in high entropy.
Yes.
But they say like, but it's order L12.
Yes.
How?
Well, if the host lattice is L12, but still the constituents occupy the L12 sites at random, you're calculating it correctly. If not, if let's say in the L12 structure, certain sites are preferentially occupied by only one constituent or 2 constituents, then the configuration entropy is reduced. So it doesn't matter on which crystallography the host lattice has, but it's the occupancy ratio. Like if it's 1/5 for all 5 elements for each lattice position, then it's correct that you calculate the configuration entropy just by the statistical entropy term. If there is the occupancy is preferred for some atoms, some constituent on some sites, then it's reduced. Then you are not allowed to do it in this simplified approach, because the probabilities will not be equal for each site and each element. Yeah, and then we discussed already severe lattice distortion, sluggish diffusion. They are correlated together. This one is not so clear for me whether it really exists. And this is what we will be dealing with. Is diffusion sluggish or is it not? Now this is going back to thermodynamics of alloys, and maybe you all know it, how in a binary system we would calculate the entropy for 2 different cases, mechanical mixture and a solid solution. Mechanical mixture is thinking of billiard balls, right? So you have equally sized balls, different color, you mix them, and then it's basically just related to how many of the different colors you have. In real materials, when you mix atoms, you get a term which is not included in the mixing of billiard balls, which is by the interaction of atoms, because they have interaction potentials. And this is the mixing entropy term if you just look at the entropy. Obviously, the solid solution has a higher entropy than the mechanical mixture does. And this is how it's calculated. So we need to take into account different quantities if we do mix a statistically significant number of atoms, because we basically have a significant number of atoms of A type, and they have the free enthalpy of the pure A state, the same for the B, and then we have this important mixing term. And when we think of high entropy systems, we really do think of the mixing excess terms. Excess means excess over the mechanical mixture. And obviously we calculate, when we now mix the two quantities of A and B, then we get a joint free enthalpy curve, free enthalpy functional, which consists of the fractions of the pure states plus the mixing term, and the mixing term is this important part where the enthalpy of mixing and the entropy of mixing, the last one multiplied by the temperature, is entering the equation. So it means when we want to have a solid solution, then we need to have a high mixing entropy term, and it helps to have also a high temperature, so they should be high. For having a solid solution, and this should be low. Right. And we always take into account, I think you all know this, that when we want to calculate phases, we do these calculations for equilibrium conditions. So it means we minimize the G functional in order to find the state that should exist at equilibrium. Yeah, then just some things. Ooh, why is it not coming? So this is what I wanted to show. I don't know why it doesn't come. So obviously, when we calculate the entropy, we have to think of this term S, as I said, consisting of multiple different entropies, and only one is controlled by how we mix different elements, right? This is the configurational entropy part. So there is a magnetic entropy contribution, especially if we apply an external field, the same for electrical, and so on. But for high entropy systems, when we design it and when we take the number of constituents as a design element, then the configurational entropy is important, and we calculate it just as a product of the gas constant multiplied with this summation term, which goes from 1 to the number of constituents, and it's basically the molar fraction of each constituent times the natural logarithm of this molar fraction. This comes, as you know, from the Stirling approximation on statistical entropy. Now, when we look at what is a high entropy, then we basically can, or people in literature, distinguish between low, medium, and high entropy alloys just by the numerical number. How large is this delta S conf term? And if it's larger than 1.5 times the gas constant, then people call them high entropy systems or high entropy alloys. And you can see it's just, you know, when you look in the equation, you know that it's just a number of the constituents. So whether you put 2, 3, 4, 5 elements together, And if you have 5 or more, then this is more than 1.5 R, so then you are in the high entropy regime. Let's go back. Yeah, so this is just how to maximize this configuration entropy term, more constituents, so 5, 6, 7, 8, 10. It's also that you maximize, you have seen the mixing entropy or peaking at equimolar values, so you have to add constituents, but you also need to add them in rather equimolar concentrations. At some point it's no longer possible because you run into some phase space where other phases will be more stable. But one thing which is very important is how large are these mixing terms with respect to a typical mixing enthalpy, because you remember this is the governing equation, right? So it means you have to beat delta H mix in order to stabilize your solid solution. So it means the quantity of delta H mix is as important or maybe even more important. If you have a very large delta H mix, you would need to put 20 components together in order to have a term temperature times delta S mix, which beats that. Or you have to go to 5,000 Kelvin, where your material will be liquid. So it means this is really very important. And if we now look into the literature on some of these mixing values, they are tabulated, they are normally given in electron volt, but you can easily convert. And you see, for example, for niobium, cadmium, this value, 2.57 EV, means it corresponds to 248 kilojoule per mole. This is the mixing enthalpy of this material. It means you have to mix much more than 5 components to get into the same ballpark. Because if you have 1.5 R and you now take a temperature, let's say 1000 Kelvin, something like a typical service temperature for an alloy, then you just get 12 kilojoule per mole out of the mixing entropy times temperature. So 12 needs to beat 248. That's not possible. So it means this approach only works if these delta H mix values of the constituents you bring together is sufficiently low. If you are now to select a new high entropy system, what does this tell you in terms of how do you select the atoms you want to mix in order to get a stable solid solution phase, a high entropy alloy? Just from looking at the periodic table, not looking into CalFat and everything, just have a quick glance, like you have an idea or you want to create an idea. Nearly equal bond length. Yes, equal bond length. Yes. They should be very much similar, right? So normally, if we have atoms which have rather similar atomic radius, Goldschmidt atomic radius, if the valence electron concentration is rather similar, this gives rather similar bond lengths, then the probability is higher that they would mix at low delta H mix, which means the probability is higher that you can mix them in one solid solution phase, making a higher entropy system. This is why, for example, cobalt, iron, nickel, chromium are great. because they are so equal. The manganese is kind of something which sticks out and stands out because it has a completely different electron contribution, has a different melting temperature. The size is not so different, but it still fits just barely. But from the 5 elements in the Cantor alloy, this is the one which limits the stability of the single-phase solid solution because it's more different than the other 4. Right? So this is, when you look at it, a very important design concept, basically coming again from interatomic interactions. And these are just the mixing enthalpies. So these are just the mixing enthalpies. There is also, but a very high mixing enthalpy either in a positive or negative way gives either rise to phase separation or to compound formation, depending on positive or negative direction. Both is bad for high entropy alloy formation. Then also there are the formation enthalpies of the intermetallic compounds to be reckoned with. They are tabulated in different tables. They are often even higher than the mixing enthalpies I have listed here. And so also if an intermetallic compound with a very large value but negative, very large negative value of the formation enthalpy is present in your system, it will form and it will beat configurational entropy each time. So you, for example, in an aluminum-nickel system, the aluminum-nickel phase is so stable, it will always form. And if you can prevent it by some clever processing, you look in the short-range order, it will still be the aluminum-nickel phase. Nothing you can do about it. Right? And this is why you have to select alloy systems according to really the interatomic interactions, and fortunately enough, pairwise atomic interactions are rather sufficient to get a good idea on what could you mix in order to get a high entropy alloy system. You don't need to know about 3, 4, 5 body problems. The 2-body problem is complex enough, and it's also good to give you already an idea of what could work, and then one has to find out. Yeah, then obviously some later stages people were making high entropy alloys already, and I think it's important to say that even early on people already found not only FCC but also BCC and HCP structures. We will talk in the course later, much later actually, also a little bit about intermetallic phases which have high entropy features, meaning that they have a more complex structure but still consist of 5 elements. That's about it. I mean, when you look into the literature, there is not so much about high entropy materials or alloys which have more complex phases like tetragonal or triclinic or so crystal structures. So it's mostly densely packed. And this is again because mostly we're talking about metallic systems, and metallic systems with rather equal properties of the constituents, and these systems tend to make densely packed structures, FCC, BCC, HCP. The more open structures are left for more covalent systems, or at least stronger covalent contributions to the binding energies. There is, however, a complete field which is outside of what we cover, which are the high entropy oxides. For functional applications like battery materials and so on, these are, I think, highly investigated. And there you obviously have completely different crystal lattices, because these are covalent systems where you have transition metal oxides and rare earth metal oxides, which are combined to a functional high entropy material. Yeah, and I think, yeah, all of these properties have received at least some coverage. I would say, if you are strict, many of these early results are also a little bit biased because people wanted to find much better properties for high entropy systems. This is something like the sluggish diffusion. First papers were all show, yes, sluggish diffusion is there, but they were not evaluating proper diffusion characteristics. And so one has to take it with a grain of salt and really do the thinking when reading, not believing everything. But you guys are all in the PhD level, so you know that you cannot believe everything that's printed and published. So one has to be careful about what to believe and what not. Today, we are really using at routine CalFAT, also for multiple constituent systems, and also density functional theory. As you see, many of the papers include theory and experiments. And what do you think, what is the largest set one can do DFT on? How many atoms can we really calculate in a rather almost ab initio way? Very good. Yes, 50, maybe 100 can also be done by somebody who has access to a very strong supercomputer. If you think now about this, doesn't that worry you? It worries me a lot. How to introduce a dislocation? A grain boundary, a phase boundary with some faceting, some periodicity, which is maybe just 10 nanometers? Impossible, right? So we are still calculating basically on the scale of an elementary cell, maybe 10, I don't care, right? But it's still, we have to really think when we read these papers, they are good, they are perfect, they are, if they are done well, we learn a lot from them. I'm not criticizing them, but just the method in itself has still restrictions. So because of computational time, right? That we can only focus the detailed, almost ab initio calculation on such small volumes that it's it requires your training, which you are getting now, in order to make the step and transfer the knowledge obtained locally and transfer it on the material scale, which is not 50 atoms, but which is maybe 500 million atoms at the least or more. Right? And so this is something one has to keep in mind. Nice that we get this insight on a very local scale, but it's very difficult and it requires a lot of experience in order to transfer it onto the material scale. Yeah, then we do all these nice characterizations, going more and more to the size scale of DFT. Sometimes we forget that also the larger scale is important. So I guess this is also something which makes it easier to write papers for high impact journals, but maybe the outcome for society is not so large a benefit. But that's my experience, my personal opinion. So don't take it too seriously. Yeah, and this is I think a very nice and very complex graph showing you properties which have been explored for high entropy materials, not only alloys, but also, for example, oxide systems. And I think it shows really a lot of research opportunities for the future, because there have been some sporadic attempts at looking at these properties, but they were not really going up to covering large depth. Specifically, if you think of properties like coatings. People have just started, right? But this is something where you can also see cost can be balanced with property. Radiation resistance, a very strong research area right now in Europe, because there is this high defect storage capacity coming in, and I mentioned earlier. And if you make this material sufficiently fine-grained, you can basically make it in terms of kind of self-healing or defect-resistant by not falling apart if you introduce a large number densities of defects. And if the number density gets higher, then the defects are sufficiently mobile to find the next sink, which is probably a grain boundary or phase boundary. And so it means that you can pump in defects, but not violating the structural integrity of your material up to a certain point, obviously. There's always a theoretical limit, but this seems to be much higher for high entropy related material as for conventional alloys. Often these are also coatings. So for example, first wall in a reactor, or for beam stoppers in synchrotrons, things like that. High entropy ceramics are very important at the moment for batteries, because one could show that you can fine-tune the different properties of the oxides by this compositional approach of having many equimolar constituents, so that you can get very nice performance. People are thinking about hydrogen storage, but so far I didn't see much in terms of properties. And there was one, this one. Catalysis is, I mean, basically you often use similar materials for battery materials as for catalytic materials. There again, the holy grail is to get rid of very noble metal constituents. And so far it seems like people could tune properties sufficient without having gold, platinum, rhodium, and so on involved, to get decent performances as well as stabilities in order to use these materials. And so this is, I think, maybe I stop there, what I would see as key research trends. In quantum materials, coatings for optical properties, tunable properties, and here tunable really means by design. So taking the same base material, let's say same constituents, but just change their composition. And in this range of multi-constituent materials, this is more easily possible by going to have maybe refractive index in a certain amount. So really go for performance and use this high entropy alloying concept, but then for non-metallic materials, mostly for the oxide materials. This is a nice concept, hybrid high entropy alloys. I would say hybrid CCAs. So people are now thinking of making structural materials which can be applied by getting rid of expensive or very heavy constituents, taking a two-phase approach, going to CCAs, having two-phase materials, and add, for example, interstitial doping, like carbon as in steel, right? And so you can then much more fine-tune whether the carbon goes into interstitial sites of phase 1 or only of phase 2 or both. Introducing trip or twip effects. This is also has been shown, some works on high entropy steels. And this can give very, very beneficial mechanical properties and at sufficiently reduced costs to really make it as a material that can be applied in industry also. This is something you guys probably know more than I on. These are the new methods of how to make materials. This is mostly based on deposition from the vapor and then doing some automated characterization. I'm an old guy, therefore I'm skeptical, because when you do a thin film deposition and you want to infer from experiments in an automated way, in a rapid automated way, I hope this works, then you have to take into account that the thin film is not the bulk material. It's even not a coating, right? So the properties are much more influenced by coherency stresses with the interface, with having a very huge open surface. And so all the properties which you determine are kind of dominated by different effects that are not present in your real material. And so I would say, it's okay to get a first shot at what the properties should be, but you have to go through a second step and do proper characterization of the material in shape, quantity, and processing conditions as close to, or much more close to, the conditions you are using in your application itself. AI-driven modeling certainly is something which everybody does already, right? And it has its future. Machine learning is something which will be interesting for high entropy systems, because it's basically just saying I have a huge bag of information and I have a good sorting algorithm. But for the high entropy systems, we don't have that huge bag yet. So whether it will be as efficient as people say or not is something we should see in the future. And something which we are also talking about in the later stages of this course is how grain refinement, Hall patch relationship, going for the nanostructures, will be affecting high entropy materials properties. There also, I think, research is at the beginning. We see interesting effects. Whether they are related to real applications or not is yet to be seen. And this is something which I think is very important. I also see in India now that this is a topic which is seeing a lot of attention, rightly so. Whether high entropy systems will allow us to do more efficient recycling, or whether we have to worry more about recycling of high entropy systems, is again something that needs to be solved and investigated. I think it's more a chemistry related community that needs to go for this, because if you want to separate these very like atoms, you probably have to involve heavy chemistry, because they are not so easily separable than other materials. But maybe it is also good because maybe some critical ingredients, if we think of exploiting cobalt mines in Africa or so, are not longer needed by using different alloying concepts that can replace one of the constituents by 2 or 3 others, which would then give quantities and properties which are as good as we need them. But again, this is something I think for the future to be seen, and just starting. But I think people think a lot about these concepts. Looking at the watch, I think it's now a good time for me to